Welcome to Design Review with Chilli Dan and Kirsch Mackey. Dan has been a signal integrity expert for 25 years, and he's been designing and reviewing PCBs for over 50 years. In this review and in all our reviews, make sure you subscribe, check it out, because we will be covering different sections. We always talk about the space. Our design today is a headphone amplifier or preamplifier. So let me explain this. The headphone amplifiers, they usually run off some kind of different supply or a battery, but this headphone supply runs, well, this headphone preamplifier runs off a USB-C port for power and still uses a plus and minus 10 volts for its analog stages. The power architecture decision affects every other part of the layout, and that's where we're starting today. We're going to go through this. So here is the preamplifier. We have a headphone preamplifier. It is a USB-C power input, and we're using different voltages here, like 5 volts, 3.3 volts, 1.8. Okay, and generally what we have here is it takes in audio input, an RCA jack input right here. It buffers that, does some filtering, and then amplifies it in the circuitry. When it amplifies it, it goes to the output stage and spits it out into a headphone jack into your headphones. What's really cool about this preamplifier is that it has an OLED display to show off the cool different signals and sounds and whatnot, kind of like an equalizer. And here's the 3D rendering of the device. It's got the USB-C port, the jacks, toggle on and off switch for amplification. Okay, so they've done a lot here. There are some things left to do by the original designer, but we're going to tear this thing apart anyway or review it as is.
This is going to be a really nice example for us to talk about because of the multiple types of signals that are on the board, multiple power supplies. So there are various voltage regulators and voltage generators. And we're controlling both analog for the audio and we're controlling digital because there's a DSP microcontroller on here. So there's a lot happening, and it's in what is probably the most popular board stack, a 4-layer board.
All right. So thank you so much for that. And I'm just going to get into the tool.
So let's look at the schematic.
Awesome. And which part of the schematic would you like me to jump into?
Let's start left to right. We're going to look at the input side and watch the flow of energy through the schematic.
Gotcha. I'm into the audio input volume control.
There we go. So we've got the input on the left. You go through a couple of comparator op-amp circuits. What I'm looking for here is you see the G&D symbols. All of them are G&D, which is really good because then you don't have to try to create isolated domains and in order to keep the signals behaving properly. So these are all good. Where there is a power pin on the IC, if you'll zoom into the bottom left corner there, the marking for in this case, you've got 5 volts and several of these. At each of these power pins, it shows there's a pair of capacitors that are connected. I've got, for example, 2.1 mic caps over on the left for U20, and one's for the +5 and one's for the -5. So those need to be placed close to the IC pins, and that's sort of implied by the way it's discussed there with the pin numbers. We've got 21C, it's the same thing. You've got a couple of 0.1 mic caps. Those just need to be placed very close to the power pins as possible based on the layout. I don't know what package these devices are, but it would be, the smaller the package, the better. The other comment I'm going to look at, we're using 16 volt components here and on 5 volt rails. You need to be very careful to look at the derating curve for the capacitors that you're actually buying. What you might find is that this is not a 0.1 cap at 5 volts. It might be 0.08. So that can make a difference in the behavior of the system. So we have to look at your data sheet to make sure that you know what your working capacitance is as opposed to the rated capacitance. Let's go to the next page. So here's another layout. We've got, I see again, the same ground symbol, which is really cool. Again, the process here is he has, for each of the IC power pins, he's put a little block that shows the capacitors that are designed to be connected to here. The flow looks pretty decent in this case. Let's zoom down into the bottom left again, and we'll talk a little more about this power supply. This is probably like the earlier op amps that we looked at before. And then scroll to the right a little bit and see this bunch here. So zoom in here. We've now got some really big capacitors. These are the big charge wells that are probably on the output of the power supply. The big caps are going to be in a large package so that they can be placed farther away.
And then having the capacitors provide the energy, would you say that it reduces the amount of stress?
What it ends up being is the initial depletion waves are a feature of the switching speed of the transistor. That goes to the first capacitor and pulls energy out. The impedance of the connection between the IC and the capacitors is fairly large. So the switching event is going to pull all the energy out of that. So you're going to have a very aggressive voltage drop at the switching frequency. It gets to the capacitor. There's a lot of energy in this capacitor compared to what's in the dielectric of the PCB. So I'm going to pull a small percentage, even if it's aggressive, maybe 10% of the energy pulled out of the capacitor by the action of the depletion wave and then becoming a sourcing wave. So the voltage drop as a result of that is much lower than what I'm doing as I'm pulling energy out of the dielectric between the IC and the first capacitor. So the next depletion wave is no longer a feature or a function of the IC. It's created by the drop in voltage in the capacitor. So now I've got a 10% reduction in voltage, and my depletion wave is now not as aggressive. So I've reduced the voltage drop that I'm going to be sending upstream to the next node, and the frequency is going to be a function of the package size of the capacitor, not a feature of the IC geometry. So I've lowered the frequency and I've reduced the voltage drop. So people like to think about that as ripple. So I've reduced the ripple happening both in frequency and magnitude. And then that energy will go upstream to find another capacitor or another place where energy is stored. If it's a bigger charge well, it's going to take it even smaller. So when you look at what happens to a 47 mic, in fact, this is a bank of 47 microfarad caps, it's going to be maybe 0.001% of the total charge. So the voltage drop is going to be much, much lower. The package is larger, so the frequency gets much, much lower. So we've dropped the voltage and the frequency as it interacts with the next capacitor. And my goal with the power supply design is to reach pseudo DC so that the switching speed of the wavefront that I'm dealing with is extremely low. It's very low frequency and it's a low energy. And the other thing I want to note is that the reason you look at a 20th wavelength for the first node is I can get a whole lot of waves going back and forth during the time it takes me to go from the small capacitor and find the big capacitor that's farther away. So if the first capacitor is a 16th of an inch, it's 20 picosecond round trip. So I go 10 picoseconds there, drop the voltage in the capacitor, that starts the next wave going upstream. Well, if that thing is an inch away, then it takes 16 times longer to get there. So before I've even gotten the first depletion wave has made its way to the second capacitor, I've got a whole lot of activity happening in this first space. And then, but each time, every 20 picoseconds, there's going to be another depletion wave. So I call it the bucket brigade. So the buckets are running upstream looking for energy, finally get to the capacitor, and then make its way back. So, it might be 100 picoseconds, depending on how far away it is. The job of the designer is to make sure that the closely placed capacitors that are within that 20 picosecond round trip space have enough energy to survive until we start to get energy from the capacitor upstream.
Oh,
So I need to be able to make sure there's enough charge here to survive before I can finally start getting energy from the capacitor. And we haven't even gotten to the power supply. It doesn't know what's happening yet.
mm,
The energy's still that next one. So for the 47 mic caps, it's got to go find a voltage regulator, and maybe there's a capacitor there. So this can be, nanoseconds or longer before the power supply is even seeing that there's any need for energy.
wow.
So it's really important to understand that whole process as you're trying to create a power distribution system that will survive and work.
Fantastic. Thank you so much for that crash course, because, these multiple capacitors, they serve multiple purposes here beyond just.
Each one has a completely different job, and we don't think about it that way. So this all looks good. We've got the output, it looks like on the right-hand side where you've got your headphone jack plugs into there. So let's go to the next page.
Okay.
And see if we can wrap up the schematic portion of our review. So again, single ground domain, I like that. It's very easy to manage. This page is pretty straightforward. I don't see anything new that we want to talk about, other than that these ICs are going to be switching faster than the op amps and the power transistors. So again, placement is going to be a little more critical. I guess zoom up into the middle IC there.
Okay.
And look at, again, I'm focused on power because power is the absolute foundation of your board. This is something I want to point out. In the data sheets, it doesn't always tell you how fast these IOs are switching, or even what the geometry of the IC itself is. And you need to know that, because that tells you what that critical 20th wavelength is. If you don't have that in the data sheet, you're designing a product that's going to be using this. You would most likely need to buy an evaluation board and measure it for yourself. Understanding the nature of what you're trying to feed and what kind of signals are going to be coming out of that. Does this need to have control impedance? That's all a function of that wavefront. What's the switching speed of the transistor on the IO is, and then how far apart can I have these two devices before I need to start managing the impedance to prevent ringing? Okay, next page.
Okay, I'm going to leave the sheet and go in from the digital section into the power section.
Okay, so this is great. So we've got still a single ground. I'm happy with that. Zoom into the upper left-hand corner. Let's look at that. So there's a power switch that allows me to pick where the power comes from. I'd want to see that 4.7 gap close to the connector. Also would probably want to see a small 0.1 gap at the connector. So if there's any kind of interference that's being applied to the wiring harness, you want to catch that in a small package capacitor, because you don't want that energy to be coming onto your board. And capacitor is your best bet at trying to prevent that. The next thing I want to see is this is an inductor. We do not know where pin 1 is. In all cases, pin 1 of the inductor needs to touch silicon. So in this case, I would want pin 1 to be on the right-hand side, because coming from the outside world, that's not where the most aggressive wave is going to be coming from. It's going to be when this IC switches, it's going to cause a drop in voltage, and that drop needs to find the inside of the inductor. If it's a single winding, it doesn't really matter. But if it's a multiple winding, you want to have the energy go inside the tunnel, so that as that changing E field is creating its changing H field, the E to H conversion, that is inside of the wires. So as it moves its way through that tunnel and finds its way to be finally on the outside of the inductor, the amplitude of the change and the wavefront have reduced in frequency. So this, again, allows me to have better EMC performance and better magnetic storage of the energy, because I want the E field to be affecting as much of that metal in the inductor as possible. I've seen boards fail with having the inductor in backwards in this particular type of application. Okay,
Oh,
we can zoom out again.
thank you. Yeah, that's very helpful. And I see that pin 2 is on going into the silicon instead of pin 1, so they'll have to flip it. Okay.
Yeah, so that's why having it as part of the symbol both on the schematic and in the silkscreen. Let's do your analysis. Well, this is a voltage regulator. Again, we've got a couple of big capacitors, a 6.8 picofarad. That's probably something the manufacturer's recommending. It's 100 volts, so you have to be conscious of what the effective capacitance is. This is 12 volts. And then you've got a couple of 25 volt, 10 mics. It's not so bad on the larger values, but you're going to, again, need to be concerned about what is the actual capacitance, the working voltage. L3 is another inductor there on the right. Pin 1 needs to be at the top because that's where the depletion wave is going to be coming from. Okay, we can zoom out.
Okay.
I think that's pretty much just take the discussion and apply it to all the various circuits. Next schematic page.
I'm leaving the sheet and going into the USB-C input.
Okay, zoom in there to the connector. So USB-C sometimes has shielded, sometimes is not. We see that there is a shell on this connector, but in this implementation, they have not chosen to isolate that. So there is no chassis or shield ground implemented here. They use a single ground, tied them all together. We've got the power supply coming in. There's a transient suppressor, and then there's a 10 nanofarad and then a 4.7 microfarad capacitor. I would strongly encourage them to draw the schematic so that there is a capacitor right at the connector pins, because until the energy sees a structure, it's still wiring harness. So even though there's a transient suppressor there, diodes respond in nanoseconds. How far does the energy travel in a nanosecond on a circuit board? 6 inches. So before the diodes wake up, whatever's going on is already gotten across the board. A capacitor sees the energy instantly. So I would suggest that they put a 0.1 mic cap. If they love these 100 volts because it might be a reliability issue, I would put one close to the pins on the A9, B9 pins before the transient suppressor. Capacitors catch and release bubbles of energy. Very little heating occurs. They don't get damaged. They don't bypass anything. They provide a low impedance, high capacity storage space. They take that bubble of field that's on a noise impulse and release it back into the wiring harness. The diodes, the way they deal with transients isn't, again, it doesn't bypass anything. They convert that energy into heat. So over time, diodes can end up being damaged. So capacitors are your best friend. The diodes are there for some heavy lifting if there's a really big impulse of energy, and you can do that. And then the 4.7 mic cap is important because you want the energy that you're going to consume on the board to be sourced from that big capacitor because it's closer to the voltage regulator. The wiring harness is infinite. It's 3 feet, 8 feet, who knows how long it is. So for a request for energy from this switch here that's driving energy into the board to find its way back to the power supply takes forever. So I want to have the wiring harness and the source of energy coming in. Their job is just to refill the 4.7 microfarad capacitor. That capacitor's job is to supply energy for the board because it's much closer. So we want to make sure that once this bucket brigade starts, that there's enough time for the depletion waves to find their way all the way over to the wall wart, or whatever the other computer that it's hooked to. So that has to be able to survive how long it takes for me to go get energy from the other end of the cable. So I always want to have a large charge well at this point, and that's where the energy is going to be used to supply the board. And on the output side, there's a big 68 microfarad a couple of them. So we're trying to put a whole lot of energy in there. I might even want to see that 4.7 be larger than that. But this is taking the voltage and supplying it here. So then the two 6.68 mic caps, their job is to now supply the USB 5 volt switch energy, because it can't come from the 4.7 and it can't come from the wiring harness. So that's the energy now that we're going to use to supply the board. And so they need to be sized well enough so that everything that needs USB 5 volt switched is going to be able to get that energy from those capacitors. And then this switch's job is the voltage regulator's job is to take energy from the 4.7 cap and stick it in the 68 mic caps. So it just takes the energy from one and delivers it. This looks like it's a linear regulator, so it's just going to allow that. And whatever's happening, again, this guy, a linear regulator works by not by converting a fixed amount of the energy into heat. Voltage drop is just taking that energy and turning it into kinetic energy. And then there's another inductor. In this case, it's across the IC. It doesn't necessarily matter. I'd have to know the internal workings of the IC itself. Which is going to be the sourcing switch node, and which is going to be the receiving node. And that would have to do with what the topology inside the IC is. So we can zoom back out again. And this all looks pretty good. Next page, I guess.
Okay, so thank you for that. We just came out the USB-C input, and now we're going to last page, the digital signal processor, or DSP.
Okay, this is probably the smallest geometry device on the board, and its job is to basically look at the input analog signal and then convert it into something that will allow you to do some processing, noise cancellation possibly, or adjusting of the frequencies of that energy, because you've got a D to A converter on there. So you're modifying the analog signal and then driving the display. So it's going to be able to pick different frequencies and drive bars on the OLED display and let you see what's happening. And in a typical, inductor or a spectrum analyzer type approach for your energy. And this is, again, we want to focus on the fact that there are capacitors here. I think the fact that it's drawn like this, let's zoom into the upper right-hand corner of this IC, of the DSP up there. So there's a 0.1 and a 47 mic. So the 0.1 needs to be close to pin 40. So how I would draw this, because of the way it's connected, would actually flip this over and put the 0.1 first and then the 4.7. Again, always put the smaller cap first in your schematic, and then use that to encourage yourself to put the smaller cap closest to the ICs.
Not to make it too long, but I got to ask this question. What happens if you put the bigger capacitor closer to the chip?
The bigger capacitor's got a larger body, so the space between the leads is much larger. So the energy per wave cycle that can go in and out of that interface between the printed circuit board and the capacitor dielectric is going to be less energy per wave cycle. So that's what I look at when I'm doing a design review for any type of product. You want to start at the schematic and look for things that can be done there. Make those changes to the schematic. And again, the earlier in the design flow that you can do this, the better. And that way, when you export this or import it into the CAD tool for the layout, that you've got all these things that are corrected and prepped for improving the results of the layout. So this is my approach for schematic review, and I hope that it's been useful. So this is the end of segment 1, and we hope everybody remembers, no matter what you think, it's always about the space.